December 26, 2004, a magnitude 9.1 earthquake ruptured the Sunda subduction zone north of Sumatra. The resulting tsunami swept across the Indian Ocean basin in 11 hours. It took over 220,000 lives in 14 countries to become the worst tsunami disaster in human history. Why was this horrific natural disaster a surprise to the scientific community and nations of the region? From 1946 through 2003, all massive tsunami-generating subduction zone earthquakes occurred around the Pacific Ocean. Furthermore, it appeared that some subduction zones had convergence rates too slow or subducting plates too old to produce earthquakes greater than magnitude 8.5. The Sumatra 2004 and Japan 2011 earthquakes taught us that, given enough time, perhaps all subduction zones can produce devastating megathrust earthquakes and deadly tsunami. Let's dig into the science of the Sumatra 2004 earthquake and tsunami so we can be better prepared at all subduction zones. At the Sunda Trench, the Australia and India plates subduct beneath the Sunda Plate. At the southern part of the Sunda Trench, Australia plate motion is perpendicular to the trench, but to the northwest becomes oblique to the trench. Farther north, India plate motion is highly oblique to the trench. This results in slip partitioning, where relative plate motion is divided into two parts. On the megathrust, slip is nearly perpendicular to the trench. Trench parallel motion of the Sumatra and Andaman forearc slivers is accommodated by strike slip on the Sumatra, West Andaman, and Sagang faults. The Andaman forearc sliver is recognized as the Burma microplate. In the preceding century, only 4 magnitude 7.7 or larger earthquakes were recorded by seismometers on this subduction zone megathrust boundary. If we go back to 1797, 3 great magnitude 8 or larger megathrust earthquakes occurred on the Australia-Sunda plate boundary, but none occurred on the India-Burma microplate boundary. Many considered subduction too slow to produce a great earthquake on that plate boundary. They would be proven wrong. The December 2004 earthquake initiated at 30 kilometers depth west of Sumatra and ruptured northward for nearly 10 minutes. Computer models of displacements on the plate boundary were derived from analysis of seismic waves recorded by the Global Seismic Network and GPS observations at monuments reoccupied following the earthquake. For example, this model shows how far and in what direction the overriding plate moved during the earthquake. Maximum displacement off northwest Sumatra was over 20 meters, and displacement decreased northward along the rupture zone. A variety of observations document vertical displacements caused by the earthquake. In the Andaman and Nicobar Islands, satellite images show some fringing coral reefs were raised above sea level while others sunk. For example, North Sentinel Island was uplifted while Rutland Island, only 40 kilometers east, sank. On the northwest shore of Semeolue Island, this coral head was uplifted 1.3 meters. Plotting shoreline changes along the rupture zone locates the line between uplifted and downdrop sites passing through the Andaman Islands and west of the Nicobar Islands. GPS observations of vertical displacements document how islands west of this pivot line uplifted by almost 2 meters, while the Nicobar Islands subsided by up to 3 meters. This tilting of the seafloor and islands riding on the upper plate is a signature of a great megathrust earthquake. As the earthquake progressed northward from the epicentral region past the Nicobar Islands, vertical motions of the seafloor displaced a massive amount of overlying seawater, producing a 900-kilometer-long crest of the sea surface on the west and trough on the east that spread into the 2004 Indian Ocean tsunami. Notice how the trough of the tsunami moving east across the shallow Andaman Sea travels more slowly than the crest heading west across the deeper Bay of Bengal toward India and Sri Lanka. 10 minutes after the earthquake started at 7:59 a.m. local time, the ocean withdrew from shores of northern Sumatra. At Banda Aceh, the ocean receded more than 1 kilometer from shore. Very few residents recognized either the prolonged ground shaking or the rapid drop in ocean level as natural tsunami warnings. Then, at 8:20 in Lotna, the ocean advanced in the first wave. The largest second wave arrived at 8:44 a.m. in Banda Aceh, inundating the coastal plain up to 10 meters deep and 4 kilometers inland. At Lotna, maximum flow depth was 30 meters, and run-up at a sea cliff reached 51 meters, the highest measured run-up in human history for an earthquake-generated tsunami. As shown in satellite images of Lotna, almost all buildings were destroyed on coastal lowlands of northern Sumatra, overrun by the tsunami. In western Thailand, residents and vacationers did not feel ground shaking from the earthquake because they were too far away. When the tsunami arrived about 2 hours after the earthquake, people on the beaches saw the ocean recede from shore, but again, very few recognized this drop in ocean level as a natural tsunami warning. Tide gauge records indicate the ocean level dropped for about 25 minutes. Then, over just a few minutes, the ocean rapidly advanced back to and beyond shore as the first wave inundated coastal lowlands. Along the coast from Phuket Island north to Myanmar, a series of withdrawals and inundations followed with tsunami heights from a few meters to almost 20 meters. Because the tsunami arrived at high tide, initial waves produced inundation depths nearly as deep as measured tsunami heights, and tsunami destruction was much worse than would have occurred if the tsunami arrived at low tide. Comparing before and after satellite images shows coastal lowlands up to 4 kilometers from shore stripped of vegetation and heavily damaged. On the west side of the Bay of Bengal, people in Sri Lanka and southwest India also were too far away to feel earthquake ground shaking, and few noticed the initial 1.5 meter high tsunami wave crest that arrived between 2 and 2.5 hours later. Many in coastal lowlands did notice the following drop in ocean level, but few understood this natural tsunami warning. The second and third waves arrived with heights in Sri Lanka up to almost 9 meters, run-ups locally over 12 meters, and inundation distance reaching 2 kilometers. The tsunami wrapped around to the southwest coast, where it swept over a passenger train, causing more than 1,000 fatalities, the largest rail disaster death toll in history. Although there is no written history of when the last comparable-sized earthquake and tsunami occurred across this region, a history written in sand provides evidence that it was over 600 years ago. On Thailand's Pratong Island, the 2004 tsunami sand overlays an older tsunami sand sandwiched between peat layers. Radiocarbon dates bracket the age of the older tsunami sand between 1300 and 1450 CE. 2 sites in northern Sumatra have tsunami sands dating between 1290 and 1400 CE and younger than 1366 CE. Uplift of a marine terrace in the Andaman Islands occurred around 1400 CE, while coral growth rings precisely date an uplift of northern Sumatra Island in 1394 CE. If all of these tsunami sands and uplifts were produced by a single predecessor to the 2004 Sumatra-Andaman earthquake and tsunami, that event occurred in 1394 CE. With increased numbers of broadband seismometers and GPS stations around the Indian Ocean, and installation of tsunameters to measure resulting tsunamis, the elements of a tsunami warning system are now in place. In principle, warnings of tsunamis generated by subduction zone megathrust earthquakes can be issued within minutes of earthquake initiation. Even for areas near the earthquakes, 15 to 30 precious minutes of warning can be issued. Still, it is critical to understand that ground shaking lasting more than 30 seconds and unusual ocean level changes are nature's tsunami warnings to move away from the ocean to high ground. On Sumatra Island, the village of Langi was destroyed by the 10-meter-high 2004 tsunami, but no one died. Oral history of an earthquake and deadly tsunami in 1907 was passed down through generations in the word smong, meaning the ocean coming onto the land. The 800 Langi villagers had only 8 minutes after the ground shaking to reach high ground before the tsunami arrived. The collective memory of the people saved hundreds of lives. The 2004 Sumatra-Andaman earthquake and tsunami delivered a powerful and tragic lesson that we should plan for tsunami-generating earthquakes on all subduction zones. Tsunami education and preparedness drills can save tens or even hundreds of thousands of lives and should be part of life in coastal communities worldwide.